Hello, welcome to our semiconductor education program. I'm Vincent Chang. In this lecture video, I'm gonna present MOS Cascode Current Mirror Part 3, Simulation. This is an interesting lecture. Not only is hands-on, but also it's intellectual. MOS Cascode Current Mirror Simulation. The circuit on the right-hand side is the cascode current mirror. On the left, it shows the code, the SPICE simulation code. So pay attention to the command. .dc is the DC switch command. Switch who? The output voltage from 0 to 12 volt with a step size of 10 millivolt. 0 to 12 with a step size of 10 millivolt, and this is the result. See, the horizontal is VO from 0 to 12. The vertical is the IO, output current versus output voltage. It goes like this. It goes like this. The output characteristic of MOS Cascode current mirror. I strongly encourage you to try this by yourself, to play around simulation tool. Any tool is good, as long as you can harness the software. So just try this, just get some feeling, get some hands-on experience, all right? Simulation. And then we are gonna go a little bit deeper and ask you a question. For example, when VO decreases, and then it's like the devil is gonna say hi and wave hands, right? Come and fall. Right? Come to the forbidden region. So the trial region, the falling region, is the forbidden region for the current mirror. But let me ask you, who falls first? The brother, right? The output brother, Q2 and the Q4. So who falls first? Which MOS leaves the saturation first? Seriously. Which MOS leaves saturation region first? This superficially looks kind of easy, but you really, if it's classroom setting and I suppose I'm on stage and I ask this question, some people will raise hand, say M4, of course, because it's on the top. But who knows? Because maybe the one on the bottom said, other students said M2. But most of the students just sit there and do nothing because they don't know how to respond. They don't know what's going on. They don't know how to think. This is not very easy. Seriously, because you have to, when VO goes down, you have to see not just VO changes, but also the source, the drain of the Q2 also goes down, right? And also you have to consider the VGS2 and the VGS4. So this is a little bit complicated because it involves a kind of complicated interaction between many variables. So in this kind of setting and the situation, SPICE is very, very applicable and useful. So you can try to simulate this circuit and get this result and try to dig in. So how to dig in, do the analysis? Just probe the VGD. The blue one is the 2 minus 4. Node 2 minus node 4 is the VG minus VD of M4. Because when VO goes up, let me pull out my video. When VO keep going up, keep rising, going up, VO is the V4, all right? The node 4. Node 4, okay? Watch carefully. So when VO goes up, then naturally the difference will goes down like this. Right? So this curve shows the VGD of M4. And then you probe 3 minus 5, the green one. The 3 minus 5 is the VG gate voltage minus drain voltage of Q1, Q2. It goes like this. Different, right? And then you put on a straight line like this. Threshold voltage. Let's say threshold voltage is 1 volt. You got two intersecting points. So now the answer kind of emerge, kind of unveil. It gets clear, more clear. So you probe, you take the two data. One is 7 volt. The other one is 4.47 volt. So the answer is M4 falls first. So the top, the one on the top, the M4 leaves the saturation first. M4 enters into trial region first. Why? You see this. When VO goes down, the intersecting point, the brown point, on the right-hand side represent what? Put down this on your note. VGD less than VT. If you are familiar with the characteristic of MOS semiconductor device, then you should be able to know this is the constraint, the condition that for transistor operate in saturation region. VGD is less than VT, saturation. On the left-hand side, on the other side, is trial. VGD is greater than VT, trial. And then let's focus on the green one. On the right is what? So M2 stay in the saturation. On the left, M2 fall into trial region. Let's superimpose the two simulation together. And then you see 3 region, right? The first above 7, both transistors stays in saturation. 4 and 2, M4 and M2 stay in the saturation. And then M4 say, goodbye, saturation, I'm going to trial. At this time, M2 stay hands in the saturation region. Hand the saturation region. Still remain in the saturation. The zone in the middle. The zone in the middle. So M2 enter trial first, while M4 enters trial first, and M2 stays in saturation, the second zone. So on the leftmost zone is both fall into the trial region. All right? So saturation, and trial, saturation, and trial. The one on the top is M4, the one on the bottom is M2. Again, let's do it again. So saturation, when VO goes down. So trial, saturation, and trial. So here's the takeaway. You have to have the sense of the changing mode. So very likely it's not fall into trial region simultaneously. All right? So someone is going to fall first. In this case, 3 region. The first one, both in the saturation, and then M4 enter trial first, M2 stay in the saturation. And then on the left is both transistor enters saturation region. The learning objective for this lecture video has twofold. Number one, I hope you can get some hands-on tool simulation experience and then try to dig in, use the tool, and get some intellectual insight about how the circuit is working, either normally or going into the forbidden region of the current mirror. So this is the end of the lecture video. I hope you enjoy it. Thanks for watching.